Non-integrable, non-integrable, no. Non-invertible symmetries and scattering amplitudes.
All right, thanks, Kolya, for the nice introduction. Also, thanks for the organizers for organizing this very nice event. And actually, I realized that it's been 5 years since I came to Brazil last time. It was before COVID. So today I'm going to talk about the recent work that we put out in March together with Christian Coppetti, who is in Oxford, and Lucia Cordova, who is in CERN. So the punchline of my talk is the following. So the punchline is that in some series with non-invertible symmetries, I'm going to explain what that is. Crossing symmetry of the S matrix gets modified. So this is a kind of standard crossing symmetry of the S matrix. So if you have some a red particle scattering against a black particle, and if you swap T and S, that becomes the picture which gets rotated by 90 degrees. Normally, if you swap T and S, you can actually relate these two amplitudes. But in some series with non-invertible symmetry, this is not true. That's what we found. And let me also give you a bit more details of what I mean by in some series. So today I'm going to focus on integrable flows, starting from minimal models in 1+1 dimensions. So those, and then in particular, the flow to the gapped phase. So it's a massive flow. And that's the series that I'm going to talk about. And important point is that it's not that we just lose the crossing symmetry completely. The correct way of phrasing it is that you actually, the crossing symmetry gets modified. And then important point is that modification is characterized by categorical data of non-invertible symmetries. So I'm going to explain, so there are a bunch of jargons, so I'm going to explain what all these mean in the next 45 minutes. So let's start by explaining what is non-invertible symmetry. So recently there have been a lot of discussions about generalization of the standard concepts of the symmetry, and all of them basically is rooted in the observation that actually the symmetry operators in quantum field series is just a particular case of some topological operators. So let me be a little bit more concrete about what I mean by this. So if you have some a conserved current, then you can integrate conserved current along a codimension 1 slice, and then if you exponentiate it, you get basically the charge operator. So what you would write is you do this on the codimension 1 slice, then you get a charge operator. And the important property of this charge operator is that basically you can integrate this object on any surface, and then this object is invariant under the smooth deformation of the surface. And that is basically coming from the fact a d star j equals 0, so which is a current conservation law. So you can just change it in an arbitrary shape. So in particular, if you start moving this in time, this invariance basically means the charge conservation law. Okay? However, once you realize that this symmetry operators are just a particular case of topological operators, then you can ask what is the meaning of other topological operators, because there are bunch of other topological operators, typically in QFT, which are not associated with a net occurrence. And what people realized recently is that you can actually view those topological operators also as a kind of generalization of the symmetry. So, and importantly, there is some difference between the general topological operator and then usual symmetry operators. So if you have a usual symmetry operator, important property is that you can multiply two symmetry operator, by which I mean you just draw a line and then put them all together. And if you do this, typically you get another symmetry operator, GC. And this multiplication basically is a group multiplication. group-like multiplication. What I mean by this is that like these GAs are basically valued in some element of the group, and then this is just the same like as how you multiply two elements of the group. Okay? However, if you consider more general topological operators, then this right-hand side gets slightly modified. And in particular, people actually analyze what are allowed structures of those fusion of the topological line operators. In 1 plus 1D, like this is going to be a line operator. And that is typically given by this kind of expression. So if you have two line operators, if you multiply them on the right-hand side, you get a sum with some coefficient, NABC and LC. So the fact that you get a sum is a crucial difference from the usual symmetry multiplication. And this is, in the literature, this is often called fusion category. Okay? And one important property of this is that this is just, this is some number, but it has to be positive or a non-negative number, non-negative integer actually, because like I don't have time to explain this, but this number actually has an interpretation as a dimension of the Hilbert space, so it has to be integer and positive. Okay, so those are basically like what non-invertible symmetries are, and then like these non-invertible symmetry, especially the fusion category in 1 plus 1 dimensions, are characterized by a few set of data. So in order to specify them, you need to specify certain like data of the fusion category. So the first thing that you need to specify is a fusion coefficient, which is precisely this NABC that I wrote over there. So as I said, NABC controls how you fuse the two line operators. But in addition, this NABC controls whether you can form a junction of the three different lines. So if NABC is not 0, then you can have a junction connecting line A, line B, and a line C. Okay? And in the rest of my talk, I mostly focus on the case in which NABC is 1 or 0. And another important data is what's called quantum dimension. From the quantum field theory point of view, this is just an expectation value of the circular line operator. So this is basically what people call quantum dimension. Okay? And so this quantum dimension, in the group-like symmetry, it's always 1. So in the standard symmetry, it's always 1, precisely because like you can just like shrink it, and then you get the QFT without insertion. But in the non-invertible symmetry case, oftentimes like the A's are a little non-trivial. For example, it becomes a square root of 2 in the what's called Kramers-Wanier duality defect that I'm going to talk about. And also, there are also the one which gives you the golden ratio, which is often called the Fibonacci fusion category. So this is the second important data that characterizes the fusion category. And the third important data is what's called F symbol. So what is F symbol? As I already said here, you can actually form some networks of line because you have junctions. And the F symbol basically means that you can relate different topology of networks. So let's imagine that we have like this network of line with X here. You can rewrite this into a sum of Y, where you have F A, B, C, D, X, Y, and A, B, C, D, and here you have Y. So this A, B, C, D, this F is basically what people call fusion coefficient, sorry, the F symbol. And so so this is a kind of like analog of 6J symbol which shows up in conformal field theory, which relates the conformal block in one channel to the conformal block in the other channel. And furthermore, important thing is that all these data actually satisfies some non-trivial consistency condition. For example, the simplest consistent condition is the following. So we consider this kind of situation in which you have like two circular lines. And you can either shrink this B first and replace it with a quantum dimension, and then shrink A later, and then that gives you dA times dB. But alternatively, I can first fuse A and B, and then evaluate expectation value. And that is going to give you sum over C in ABC DC. And obviously, this condition needs to be satisfied for the consistency. And if you include F symbol, that's a rather a highly constrained system, and finding the kind of answer is a non-trivial question. And there are several ways of getting these non-invertible symmetry fusion categories. One way is to start from theory with G, where G is a finite non-abelian group. And then you gauge G. And in 1+1 dimension, if you do this gauging procedure, of course you lose the original symmetry because now the symmetry is gauged. But in 1+1 dimension, you actually obtain a new symmetry if you do the gauging. And then the new symmetry is what's called a representation category of G. So the difference between the G and the representation of G is that in the case of G, those symmetry lines are labeled basically elements of the group G, whereas in the representation of G, those symmetry lines are classified or labeled by the representation of the G. And then this is a kind of canonical example of non-invertible symmetry. And another example, then there are also a bunch of examples coming from a rational conformal field theory, or 3D Chern-Simons, considering 3D Chern-Simons theory, and then consider what happens in the boundary of the 3D Chern-Simons theory. And those often give rise to what's called modular tensor category. And the important difference from the general fusion category and the modular tensor category is that in the case of modular tensor category, there is a notion called braiding, which I didn't write here. The general fusion category doesn't have a notion of braiding, but the one constructed from this has a notion of braiding, which is basically a moving lines into a different order. And the third way, which is more mathematical, is that you can actually construct, there is a kind of mathematical way of constructing these fusion category, starting from what's called type 2-1 subfactor of von Neumann algebra. But of course, I don't have time to explain, and I'm not sure if I can explain actually. But important thing is that there is a mathematical construction, and that leads to various exotic symmetry. And one famous one is called, actually, I don't know how to correctly pronounce this, but Hagerup fusion category, I guess. Is that correct? And so this is an interesting fusion category because it has all the property to be a symmetry of the quantum field theory, but the quantum field theory realization is not fully understood yet. Okay, so now, so far I've been talking about rather abstract notion of what the non-invertible symmetries are. So now I'm going to give you the simplest example of non-invertible symmetry. So what is the simplest example of non-invertible symmetry? Of quantum field theory with non-invertible symmetry. That's actually very simple. You can actually see it already in the Ising model, or more precisely, Ising CFT. So example. So what is Ising model? Ising model, 2D Ising model, of course, as you know, it's basically some statistical mechanical model in which like you sum over spin with some Boltzmann weight, which is beta, inverse temperature, and then nearest neighbor interaction, and sigma I and sigma j. Okay, so this is of course very standard. But you also probably know that this Ising model has interesting duality. So this partition function as a function of temperature has some like a critical temperature at Tc, at which the theory flows in the IR to conformal field theory. But there is a non-trivial duality between which relates the theory at low temperature and the theory at high temperature, which is called the Kramers-Wanier duality. And which basically relates e to minus 2 beta low temperature to the tangent hyperbolic of beta high temperature. Okay? And so at generic temperature, this is not a symmetry because it's a duality transformation which relates one theory to another theory. But at T equal Tc, this actually becomes a genuine symmetry of the theory because like this map actually maps the same theory. Like this becomes a map of the same theory. So at T equal Tc, it becomes a symmetry. Okay. However, this is a slightly weird kind of like a map if you think a little bit more carefully. And that is actually, and then like you can actually see that it's a kind of non-invertible symmetry. And this is actually easy to see if you think about the vacuum structure of the Ising model. So in Ising model, as you know, that when temperature is above critical temperature, we are in the disordered phase. Whereas if the temperature is below the critical temperature, we are in the ordered phase. So what I mean by this is that if you think of this 2D Ising model as a quantum field theory, at high temperature, you have one vacuum, single vacuum. Whereas in the low temperature, you have like two vacua, two degenerate vacua, and the symmetry is spontaneous, Z2 symmetry is spontaneously broken. Now, as I said, the Kramers-Wanier duality relates low temperature to high temperature. So if you look at the action of this duality at the very, very low energy state, which basically only contains vacuum, then you can see that actually this map is 2 to 1. More precisely, if I denote this vacuum minus and then this vacuum plus, and if I denote this vacuum 0, then the map is going to be the following. So the Kramers-Wanier duality relates plus vacuum to the 0 vacuum, minus vacuum also to the 0 vacuum, but the 0 vacuum gets mapped to plus minus vacuum. Okay? And you can see that this map actually has a kernel. For example, if you start with plus minus minus, then it gets projected out under this duality transformation. And this weird property is also present if you consider theory at the critical point, for which the Kramers-Wanier duality becomes a genuine symmetry. And people actually analyze this symmetry in the old days when people are studying 2D Ising CFT, 2D Ising CFT. And then this symmetry is often called, in the math literature, Z2 Tambara-Yamagami category. Tambara and Yamagami are basically two mathematicians. Yamagami, a fusion category. And in this fusion category, you have basically 3 different symmetry lines. The first one is identity line, which does nothing. And the second one is an eta line, which is basically Z2, which implements Z2 symmetry. Of course, because we are talking about Ising model, it does have a Z2 symmetry. And the third one is the most interesting one, which is precisely this Kramers-Wanier duality defect. And so this one, and then they actually obey interesting fusion relations. So for example, the obvious one is that if you square eta, you get 1 because it's Z2. So this is not surprising. But if you square n, Komatsu duality, then you get 1 plus eta. You can also check that this relation is consistent with the map that I wrote here. And finally, n times eta equals eta times n is En. So this characterizes completely the fusion relations of the Z2 Tambara-Yamagami category. And so this gives us the simplest example of a quantum field theory in 1 plus 1 dimension with non-invertible symmetry. And my talk, the topic of my talk is about scattering amplitudes and the interplay with the non-invertible symmetry. So you might ask, like, okay, maybe we can explore that question here. But unfortunately, 2D Ising CFT is a little bit too trivial because it's basically like a free fermion and S matrix is -1. There is nothing interesting happening here. However, well, then you can ask, like, what happens if you deform 2D Ising model? Because we know that, for example, if you deform 2D Ising CFT with magnetic deformation, then you get like this famous homological for E8 S matrix. However, there is an unfortunate news that you can actually show that all the relevant deformation of Ising CFT breaks this Komatsu duality defect. So unfortunately, if you start from Ising CFT, there is nothing you can explore about the scattering amplitudes. So what should we do? Actually, like you don't actually need to think hard, so hard, because if you look at the next simplest theory in 2D CFT, you can already find interesting renormalization group flow in which, along which this Komatsu duality symmetry is preserved. So what is the next simplest conformal field theory in 1 plus 1 dimension? That is, as many people know, the tricritical Ising model, or tricritical Ising CFT. So let's talk about that. So now I'm going to give you an example of gapped flow with Komatsu duality. So as I said, you can actually realize non-trivial RG flow if you start from the tricritical CFT, tricritical Ising CFT. And deformation of those like minimal models are like well studied in the literature in the past. And there is a very famous flow which connects the tricritical Ising CFT to Ising CFT, which you can obtain by deforming tricritical Ising CFT with what's called phi 1,3 primary operator. Then it is famously known that you land on the Ising CFT in the IR. And the nice thing about this flow is that along the flow, all the Z2 Tambara-Yamagami fusion symmetries are preserved. Okay? So, and now of course, like, we know that it exists in the IR, but the important point is that it actually exists all the way from UV to IR. But this is not the theory that I want to study, because again, like I wanted to say, I said like I wanted to study the flow to the massive theory. But actually, you can easily get the flow to the massive theory, because if it is also known that if you perturb this theory with minus sign, minus phi 1,3, you can actually flow to the gapped phase. And in this case, unlike Ising model, you flow to the gapped phase with 3 vacua, 3 degenerate vacua. Okay? And so let's call it this 0 and plus and minus. And let me make one comment. Like, so this pattern actually persists. Like, instead of starting from tricritical, if you start from Ising and then deform it with plus sign, this actually precisely corresponds to temperature deformation. And so you get like a disordered phase, whereas like if you perturb with minus sign, you get a disordered phase. And this also continues in this direction. You can also start from the higher minimal models. And then you get like the vacua with four, like a theory with 4 vacua and so on. So now, the important thing is that already we know that this one preserved the non-invertible symmetry, and because we are deforming by the same operator, this one also preserves Z2 Tambara-Yamagami fusion category. And in particular, it also acts on the vacua of the theory, which are like these 3 vacua. So let me just write what the actions are. So the actions on the vacua are the following. So I wrote over there that there are 3 vacua labeled by 0, plus, minus. And the action on the vacua are basically given by, so if you consider like a eta defect, which is like a Z2 symmetry, then it flips plus and minus. So it basically like flips this picture. Whereas if you do the N symmetry and then act on the middle vacua, you get plus, plus, minus. And if you start from N and plus or N and minus, you get 0. So in some sense, like this action of vacua, in terms of like action of the vacua are concerned, it's a bit like a superposition of the disordered and ordered vacua of the Ising model. Okay. So yeah, actually, we don't have much time, right? I guess. $14, okay. So then let's move on. But like before moving on, like let me also just say a word, say by word that this number of the vacua 3 is actually also, you can also kind of like derive from the structure of the fusion category. So unlike the usual case of like usual symmetry, like a Z2, in which like both having single vacua and then 2 vacua are allowed, typically the non-invertible symmetry is so constraining that you cannot actually flow down to single vacua. And then 3 turned out to be like a minimal number of vacua you can actually have preserving this symmetry. Okay. So now let's talk up. So as I said, like so in the rest of my talk, I'm just going to focus on this flow. And this flow, as many of you know, it actually has another interesting property, which is basically the integrability. So this is why I'm talking about this in this conference. And in particular, Zamolodchikov already determined what is the S matrix of the massive excitation along this flow. Okay? So the 3 critical plus 513 is integrable. And the particle excitations, elementary particles excitation in this flow is basically kinks between neighboring vacua. So you have like a 3 vacua, and then basically kink can interpolate between this and this, or this and this, but not this and this. Okay. And the S matrix of these kinks are described by what's called RSOS type S matrix. So the reason why people call it RSOS is that because now each particle interpolates between different vacua, when you describe the S matrix, you also need to specify which vacua you are talking about. So now I'm going to use a slightly different notation in order to be consistent with the notation in the literature. So I'm going to denote this 0, and then denote this vacuum 1/2, and denote this vacuum 1. And with this convention, for example, like you can consider scattering amplitudes, scattering of the 2 kinks, and then these numbers are basically just labeling which vacua solitons are interpolating. And so now I can show you what is the S matrix Zamolodchikov wrote. The S matrix Zamolodchikov wrote is the following. So it of course depends on 4 numbers, and then it's also a function of the rapidity. And so this one, which, let me just draw a picture as well, A, B, C, D. There is some overall factor, which is a CTD factor, but that's not important. What's important is the rest. So Zamolodchikov showed, basically bootstrap this S matrix to show that the S matrix that you have takes this form. So here you have I theta over 2 pi, and then here you have square root of the same thing, dA, dC, dB, dd. I'm going to say what these are, but let me just say right ahead that right now that this is related to the quantum dimension that I mentioned earlier. I pi minus theta over 3 delta AC. And these dAs are basically some number which is related to this like a label of the vacua. And for 0 and 1, we have 1. And then for 1/2, we have square root of 2. Okay. All right. So this is a S matrix Zamolodchikov wrote. And as I said, like this flow also is expected to preserve non-invertible symmetry, like a Kramas-Vanier duality symmetry. So this should also, this S matrix Zamolodchikov wrote should also commute with this line operator. So this is like a natural thing to expect if the symmetry is preserved along the entire RG flow. But Zamolodchikov didn't really check this property because around that time, people are not talking much about the non-invertible symmetry. So we decided to check this property, and in particular for both Z2 symmetry and the non-invertible Kramas-Vanier symmetry, which is N. For the Z2 symmetry, this word identity basically relates some S matrix to another S matrix. You just like flip like a 0 and 1. And it almost obviously like it's satisfied by this S matrix Zamolodchikov wrote. But the surprise was like this N defect. So the word identity of the N defect typically take this kind of form, which basically relates one element of the S matrix to a sum of two elements of the S matrices. So this word identity is much more non-trivial. And it turned out the answer that Zamolodchikov wrote didn't actually satisfy this word identity. So something wrong is going on, which basically means that there is now a paradox. So it seems like the three principles Zamolodchikov used to bootstrap the answer, unitarity, crossing, and Yang-Baxter, is incompatible with a non-invertible symmetry. So we have to give up one, at least. And of course, like we probably don't want to give up unitarity. And also, we don't want to give up Yang-Baxter because like if you perturb, like if you do the analysis around the CFT point, you can actually show that infinite number of conserved charges survives under the deformation. And the same is also true for non-invertible symmetry. Like if you start from the UV CFT and then look at what deformation is doing, you can actually show that non-invertible symmetry is preserved. So from this perspective, the only option that we can take is to give up the crossing symmetry, at least the standard one. Okay? And in fact, like if you give up crossing symmetry, it's actually easy to write down the S matrix, which satisfies like these three properties. And so the new proposal we made in the paper indeed satisfy that property. And let me just write down for you what the new proposal is. But I don't actually need to write it down because it's basically the same as the Zamolodchikov one, but without this prefactor, which looked already probably a little bit weird to some of you.
So could it also be an interpretation problem of the S matrix? Say if you scatter not the soliton, but some linear combination of solitons?
linear combination of solitons. So you want to think of this as a, but I think these labels are really like labels of the vacua. And if you specify, then you're actually singling out soliton. So that might be a little bit unnatural, I would say. Okay. So, but of course, if you modify the ansatz, then there is a price to pay. And the price to pay is that now the crossing symmetry is modified. So let me, write it down for you. A, B, C, D of theta equals square root of dA, dC, dB, dd, S, B, C, dA of I pi minus theta. So in the case of usual crossing symmetry, this factor is 1, but our ansatz, our new proposal, violate the crossing symmetry because of this factor. And importantly, this factor is not a phase. Okay, so in the rest of my talk, how much time do I have? Including question time or without? Okay, then it's good. All right, so now I'm going to give you some derivation of the modified crossing. But it's actually like very simple, rather simple. So let me just summarize what are key inputs for this derivation. So here, I just made a proposal and then observed that the crossing symmetry is modified. But there is actually more direct way to argue for that particular factor, and that's what I'm going to explain. So the key inputs that go into the derivation is the following. The first one is the IR is gapped. But it's not trivially gapped, but it's governed by non-trivial TQFT, topological quantum field theory. And then those TQFT have precisely those line defects, symmetry lines that I was talking about. And the second important ingredient is that vacua are in one-to-one correspondence with symmetry lines. So I already said this theory has a 3 line, 1, eta, and n. And indeed, we also have 3 vacua. So the number matches, but there is something more to it. So the identification is that you can identify 1, 0 vacua, the middle vacua, the leftmost vacua with 1, and then the middle vacuum is n, and then the rightmost vacuum with eta. Then actually the action of the symmetry on the vacua becomes the same as the fusion rule. Okay? So there is a way to get the way to relate the vacuum with the symmetry line. In particular, this means that you can actually start from 0, and by acting n, you can get 1/2. And also, if you act to 0, you can get 1. So all the vacua, you can actually generate starting from the leftmost vacuum. So that's one important property. And so the third important property, which is probably the most important one, is that word line of soliton also acts like a symmetry line from the point of view of the vacua. So let me just write down it explicitly. So word line of kink, you can also identify this with a n symmetry line. This is kind of obvious because as I said, the word line of kink interpolates between 2 vacua. And then this is precisely what this n symmetry line does. Okay. So now, but this actually has an important consequence. So together with this and this, there's one important consequence, which is the following. So let's consider the word line of kink interpolating the vacua of A and B. And this, you can also think of it as some kind of like putting some boundary condition here, a boundary condition, and then kink, which is like which can be identified with n defect, and then on the right, you are putting boundary condition on B. Because if you put a boundary condition, you specify the vacuum. But I also said these boundary condition, or like a vacua, can be generated from the zero boundary condition or zero vacuum by action of the symmetry line. So which means that I have this, and then instead of like writing A here, I can write 0 here, and then I can write A vacuum here. So now it looks like this. Okay, so this is like a time. Now imagine we are in the Euclidean signature, and then I can do the kind of conformal map, mapping this like an open string to a disk. So that gives you this picture. So you have like some disk in which you put a zero boundary condition at infinity, and then here, like because it goes all the way to minus infinity, it actually forms a junction here. And the same is happening in the future. So this configuration actually gets mapped to some network of line, A, B, and N. Okay? So using this kind of identification, you can map the configuration of multi-kink states to some kind of network of line. And this like a big black circle is kind of irrelevant. It just sets the normalization, right, which we can normalize to 1. So the key punchline is like a multi-kink state can be mapped to network of line. More precisely, what I mean by this is that if you go to the extreme low energy, multi-kink states viewed from the TQFT is equivalent to the network of lines. Okay, with this now I can really derive the modified crossing equation. So now, how do we derive the crossing equation? So, of the S matrix. So normally, if you want to derive the S matrix, okay, 1 minute. To derive the S matrix, you need to do the LSC procedure. Like you take correlation function and you go to the Fourier space. But when the kinks are involved, actually this LSC procedure is not fully established. Instead, like there are like many indication coming from the flat space limit of ADS-CFT, or in the context of celestial holography, people are discussing recently what's called extrapolate dictionary. I don't have time to explain what that is, but the punchline is that you can actually get S matrix directly from some correlation function on a big disk. So let's say some correlation function on a big disk with boundary condition A, B, C, D, and then perform a suitable analytic continuation to the Lorentzian signature. And then taking some limit in which like this disk becomes infinite. So this gives you kind of like a more direct way of getting S matrix. Now, I said here equal, but precisely speaking, this cannot be equal. The reason is that, as I'm going to show in a minute, if you just draw this picture, the in states and out states are not correctly normalized. What I mean by this is that I already said that you can, like, so this, roughly speaking, define in state, and this, roughly speaking, out states. And as I said already, like, you can basically map the configuration of two particle states, in this case, to a network of lines. And which in this case becomes something like this network of line. So you have like in state corresponds to this half network of line. We have DC, B, and NN. And the out state, or more precisely the ket of the out state, roughly becomes this upper half, which is A, B, N, and D. But then, as you can see, if you compute the norm, it actually corresponds to some non-trivial network of line, which looks like this: N, N, D, B, C, C. Okay? And therefore, the same is true for outstate. So therefore, in order to get the S matrix which satisfies the usual unitarity, you need to take this analytically continued disk correlation function and divide by the norm, which is like this. So this is a norm of in-state and norm of out-state. So let's write explicitly dBCC, and then here dBAA. And then the important observation is that this one, because it's just like a disk 4-point function, there is nothing weird happening like if you rotate this picture by 90 degrees. But this one really depends on the channel that you're talking about, because if you consider the S channel, you need to draw, sorry, the T channel, you need to draw this kind of network of line. So you have a different normalization depending on the channel, and that is precisely the reason why we are going to get just one last formula. This factor, which is actually the ratio, square root of ratio of network line, BC dA I pi minus theta. So this finishes the derivation, and then maybe I should end my talk here.
Thank you.
So a quick question. So if you open like the Weinberg book, for instance, crossing is derived based on some basic assumptions. And what I didn't get is, are you saying that this model violates some of these assumptions?
Yeah.
Or are you saying that, so it's just it violates these assumptions? It's not like that you are defining this in and out states in some way that is good for your symmetry.
No, look at the, so the
what goes wrong in the Weinberg proof, for instance?
So those like a derivation of the cross-end symmetry, for example, like there is a famous work by Bross, Epstein, and Glaser, and that actually like uses the LSZ procedure. So you need to start with some correlation function of local operator. Here, like it actually already breaks down there because the king creation operator is a non-local operator.
Can you use this modify crossing in some S matrix bootstrap setup?
Yes, I forgot to mention, but like that's about upcoming work. We did do the S matrix bootstrap for Fibonacci fusion category and then what's called AN fusion category, and we indeed you can actually find the cusps like some interesting integrable series.
Elements are structure constants in the homological of Adiev algebra. So what the modified crossing bearing does it have in the algebra?
I would say it's about like how somehow you need to change some normalization of like a dagger creation operator if you change the argument I pi minus theta. I don't have a clear answer, but that's what I can say now.
So your modification doesn't change the spectrum in TBA?
Okay, so that's a good question. So if you do the periodic boundary condition, it doesn't change. It doesn't change. But we do expect it changes if you twist the boundary condition. And then that's also what we are currently exploring.
So I remember that these nasty factors, what you are talking about, was gauged away by changing the basis of the incoming states. And then they were somehow crucial when they considered these theories as some reduction of the sign Gordon and imposed some extra fractional supersymmetry. Can you comment on this?
Right. So formally, you can relate like a homological of S matrix and RS matrix by changing the base. But if you do that, for example, okay, maybe you can say like the homological answer is also correct if you use a kind of different basis. But it turns out like if you want to make sure that there is a non-invertible symmetry in the homological of S matrix, now the action of the global symmetry depends on the rapidity, which basically means that it doesn't commute with the Lorentz boost. And so that's in some sense some physical basis. And I guess like it's probably like telling this more or less the same thing as you mentioned about the compatibility with the supersymmetry.
So maybe I think part of my question is related to what Zoli was just asking. Do you see what could be the implication if you extend this to n equals 2 minimal sector?
N equals to minimal models.
Yeah, minimal models.
I guess, yeah, well, the same should apply to n equals 2 because there are Landau-Ginzburg description.
Exactly.
But okay, more than that, there is nothing I can say at the moment.
Okay, do you see, maybe you have a clue, because there are also these mirror duals, like you say, perturb Landau-Ginzburg.
Oh, okay.
Do you see what could be the counterpart that would be happening on this side? Or it's hard
yeah,
to say?
that's an interesting question, but yeah, right. But I don't have an answer to that.
All right, so I think okay, let's carry on. With our program. No.
If you just knew abstractly that some theory happened to have this modified crossing relation in its S matrix, would you be able to diagnose the fact that it needs to have these non-invertible symmetries as well? Would go the other way?
Okay.
Invert non-invertible.
Yeah, that's an interesting question. Well, that question, yeah, is also probably relevant in 2+1 dimension, in which people observe the modified crossing in Chern-Simon matter. But the argument looks similar, but not quite the same. So like there might be some kind of like a direct symmetry argument. So if one can do it, I think like we will be able to understand that example better. But at the moment, I don't know.
All right, let me ask the last question. No, is there a relation between this matrix and the F symbol? Yes or no?
Not directly.
Okay, thank you, Shota.